Okay, derivatives of logarithmic functions. Since we know the derivative of e to the x, we can easily determine the derivative of the inverse, which is ln of x. And I love this proof. I love this proof because it's shockingly simple, but it has so much in it. I love this proof so much. I'm tempted by the end of this lesson. There's two proofs in this lesson that are virtually identical. I'm tempted to just say, hey, one of them's on the test. And that's actually a gift to you. You go, hey, I don't have to wonder. I'm going to study a million things. I know this is coming. Well, let me walk through it step by step first. Me trying to convince you how lovely it is. They said try and find the derivative of ln x, which seems impossible. And I do not have to rely on h's or anything else. I just start with y equals ln x, and I'm going to do some stuff to move this around and find its derivative using weapons you have. We've got to talk about each weapon that I use, though. The first weapon is that ln is the inverse of e to the exponent of. That's an important line, and that's why I love this proof so much. I need you to know that, and I don't know that we've done a great job putting enough pressure on that idea. So let me go through it again. Adding has an inverse called subtracting. When you move adding over, it becomes subtracting. Subtracting becomes adding. Multiplying becomes dividing. Dividing becomes multiplying. They're inverses. Squared, square root, squared, which is a little confusing when you first see it. When you first tell the grade 8s that the inverse of squared is a little checky-do thing and it undoes squared, they're confused, but you're not confused. You're like, I get it. I get it now. X squared, square root. The inverse of ln is e to the power of. That's the inverse. When you move ln over to the other side, you get e to the power of. There's a deeper explanation than that, but it's actually just that simple. That's what e and ln are. They're inverses of each other. Sorry, e to the exponent of over there. Well, this just changed this question dramatically. It changed it for finding the derivative of ln, which how would we have any idea how to find the derivative of ln? To find the derivative of e, which we know is pretty easy. We just did that yesterday. Find the derivative of e, it actually turned out to be easier than power rule. You thought that was simple. Bring down the power, reduce it by 1. The derivative of e is e. Well, okay, watch over the chain rule. That's all. Just watch over the chain rule. So here's my move. I'm going to take the derivative of both sides with respect to x. And I'm going to write it dramatically like this. And again, some people might argue that I'm really not doing anything in that step except explaining what I'm going to do. I'm going to take the derivative with respect to x. And if you don't love Leibniz yet, Leibniz is basically just saying, go ahead, take the derivative, but I'm going to tell you what you're taking the derivative with respect to, so you get that d by dx in there. All right. Tune in from yesterday. The derivative of e to the y is e to the y. Then you got to go derivative of the inside. And now your implicit differentiation appears. See how beautiful this proof is? Pretty simple, not a lot going on here, but a lot of ideas all in one proof. E to the y, dy by dx. So, derivative of e to the y is e to the y, but then you got to go derivative of the inside. And when we talk about inside of an exponential, we mean the exponent. That's the inside. And then watch this. This is great. The derivative by dx of x is just 1. Yeah? One more step to get the derivative. Now, it's not done yet, but to get the derivative, one more step. Dy by dx equals 1 over e to the y. And there's so many proofs in calculus that use this method to just move things around, find the derivatives, and then you get stuck with this, though. This is dy by dx. We usually want them in terms of x, you see? So we got to go back and find e to the y somewhere out there and sub in for that, and hopefully it has just x's. Look at that. It's so good. I love proofs like this where you just go, at the end you're like, oh no, it's not right. It's not 1 over x. It's 1 over e to the y. And then you're like, doing, e to the y equals x. It's so good. It's good. Love this proof. One of my favorite all-time proofs. How many big ideas does it have from this chapter? Inverses. Taking derivatives of both sides with Leibniz. Implicit. Some substitution at the end. So good, but it's only 6 lines. It's only 6 lines. And you get a beautiful derivative. Think of all the crazy derivatives we've done so far and how long it took me to develop them. Ln, whoop, done. 1 over x. We've got to talk about chain rule when we go to take the derivative, but that's all. I hope you're getting used to chain rule. It's like, okay, times the derivative of the inside, every time. I'm doing it. I'm going for it. I'm finishing writing your test tonight. This proof or the other one from this lesson. One of the two I'm going to choose. Maybe by the end you'll go, oh, I know which one you're going to choose. I can tell by seeing the two of them. Because I'm going to do it all again if you're like, okay, I sort of get it. Oh, 1 star? No. I'm going to steal this from, my favorite prof ever. Professor Forrest at Waterloo used to 5-star things and look us in the eye and go, 5 stars, baby. This is a 5-star proof. And we knew it's on the midterm. It's on the midterm. We might not get all the stuff on the midterm, but we're going to get this proof at least, because that's the beauty of proofs, is that you're like, okay, I know it's coming. I just got to make sure I know all the steps. And I get those marks. It happens very quickly. Boy, you don't want it blank. That means you weren't listening during the lecture to 5-star this thing properly and know, hey, there's 3 of my marks right there. Yeah. But what questions do you have about this proof? If on a scale of 1 to 10 you're about a 6, where you're like, I sort of get the proof, but not really, I'm doing one just like it later in the lesson, so you can wait and see and save your questions for there. But do you have any questions about that proof? Simon. He'll say this. No, it'll just say this. Prove derivative of ln x is 1 over x. Go. Okay, wait till you see the other proof. And maybe that'll complete the answer to your question. All right? So when I say this proof, I mean this proof. Or the other one. Well, when you see the other one, you go, okay, well, it's got one extra thing really all in it. Okay? Questions here? No, it's good. Something's wrong. I feel discombobulated. Okay. Here's homework questions and stuff that you might see on the test for using ln. All stuff you've seen before. Differentiating the following. Y prime equals x ln x. You have to recognize that as a product rule. So if you're still having trouble with that, get your little squiggle out to go, okay, there's 2 different functions here. There's x and there's ln x being multiplied together. So I got to think of them separate. I got to go derivative of the first. Not so bad. Listen, I've gone back to writing my 1s like that because of ln. When I write ln, it looks like 1n to me. So now I've got, as soon as ln appears, I wasn't writing 1s like that yesterday. It's just an old habit now. As soon as I see ln, I'm like, oh, 1 looks like that now for today because ln's involved today, So just, okay, derivative of the first times the second. Even the size, you see how big I wrote that 1 to make sure I don't get confused with 1 and ln x? It's not 1x. It's not 11x. It's 1 ln x. Plus derivative of the second not bad. Not the simplest derivative ever, ln. But pretty good, really, when you think about it. Ln x, 1 over x. Okay, I got to slow it down. Derivative of the first times the second plus derivative of the second times the first. And the reason I slowed that down is that if you're still doing that with product rule, halfway through you go, hold on, let me just go through it again. Yeah, you're doing it right. That's the way product rule is. You got to go through each step or you miss something. A little tidying up, and by a little, I mean a little tidying up here. Oh. Questions? I want to rephrase the previous page for a second, just to help you with the derivative of ln, because the derivative of ln can mess people up in one way. Instead of calling it derivative of ln x is 1 over x, I'll just say derivative of ln of something is 1 over something. That's a good way to remember ln, or else you can get messed up here with what's happening here. If you're right with it with the chain rule, then this isn't going to be no problem. But derivative of ln of x squared plus 2x minus 5 is 1 over x squared plus 2x minus 5. You see, it's not 1 over x every time. It's 1 over whatever's there. Times chain rule that. So that's like dy du. I'm still trying to push that dy du, du dx stuff in there. Dy du, take the derivative of the outside, but evaluate it at the inside. F prime at g at x, just nudging along that stuff still a little bit to say, okay, I'm taking the derivative of this thing, but I'm keeping the inside the same. Then times the derivative of the inside A little bit of tidying up. At least find the common factors when they're there. And I brought that thing up to the numerator because it's really over 1, so I just put it on the top. Questions about that? Questions? More time? Who wants more time? Yes, more time. I'm on slide 2 of 6. Well, there's a couple of long slides coming, so don't get too excited. More time? It's good. Ln of cos of x. Okay, these ones that are buried inside can mess people up a little bit, and I really suggest using your hand when you get to these things to cover up what's inside and not let it confuse you. Y equals ln of cos of x, y prime equals 1 over whatever's in there. You know, if it was x in there, I'd go 1 over x. When it was x squared plus 2x minus 5, I go 1 over x squared plus 2x minus 5. This is cos x. So it starts with 1 over cos x. Secant, if we needed it to be. Then cover up the outside and go, okay, now times derivative of the inside. And I get and I haven't pushed trig identities too much, but geez. I think we've got to have this one. Will. Yeah. Got to start to have that one. It's one of those things that slip through the cracks with COVID and advanced functions and everything is using trig identities in your final answer well. We better start at least grabbing the ones that are sine or cos. Why is this better? Because it's only a single trig ratio instead of 2. That's why it's better. Yesterday there was one that had some stuff in the bottom. It was sines and coses, and they went to secants and tans. You're like, why do you go to secants and tans? Because it has no denominators now. It had only regular terms. So just got to start moving towards it. And doing the homework questions help with that because you see what they move towards, okay? So the big ones are tan, secant, cosecant. Let's see if we can't start bringing those in when we need them. Questions there? Oh, here we go. Like this is the ugly homework question. I don't know that I'd really ever select something like this for a test or exam, but it's the one in the homework I go, okay, if I can land this, then whatever Mr. Todd comes up with in the test, I'll be ready for, yeah? One over that mess. We got to talk about 1 over for a second. Let's go down here for a second and talk about 1 over. Because if you don't have this weapon down, it's sort of important you have it. I'll just do 1 over a weird fraction. Let's say I do 1 over 2/5. And let's see how that works out and see if we can come up with a plan for 1 over. And really, what does 1 over do to things? I'm going to write it a different way. I'm going to write, oh, that's 1 divided by 2/5. Dividing fractions is like multiplying by the inverse, and here I end up with 5/2. And this happens every time when you're 1 over something. What does it really do to the thing you're 1 overing? It just flips it. That's really what's going on here. When you're dividing by a fraction, you're really talking about multiplying by its inverse. So I don't know. If I write 1 over this mess, I've got a big mess in my hands. And you can do that. You can write 1 over, and then go through the steps, go 1 divided by that big mess, 1 times the inverse of that big mess, or you could just know what you're doing and do this. But that's not all. Now I got to go derivative of the inside, which is now a quotient rule with a square root in it. It's a giant, ugly mess. And so I need a new version of this. Oops. I didn't write the ln because I actually don't care about the ln anymore. I did that derivative, but I guess I need this. So a little practice on those tough derivatives in there. A quotient rule with a 1/2 power in the denominator. Here I go. True to the top times the bottom. Minus true to the bottom times top all over the bottom squared. What a mess in there. What a mess. Especially if you haven't done enough of the tough derivative homework, this will be a challenge. So let me go through it and act like you haven't done that homework, and we got to talk about this. First thing we look for is to group up monomials. There's no real help there in grouping up the monomials. Then I look for a common factor. There's an x plus 1 in both terms in the numerator. Which one do I pull out as the common factor? The 1/2 or the negative 1/2? Okay, a couple of hands going up. That's going to come up on the test. Or we run into one of these ones where it's like a positive and a negative. Which one? And why? Brad, which one? Why? The lower number. In common factors, we always take the lower number, and the lower number is going to help dramatically here. I'm going to pull out x plus 1 to the negative 1/2. Another square bracket in here. And so look at this. What's the difference in these two exponents? How far is negative 1/2 from 1/2? 1. Well, 2 halves, but 1. And why is it 1? Like it's like every time when you do these common factors, like it's always 1. Isn't that convenient? Isn't it? You're just rigging these questions up. It has to be 1. Yeah. Right from the start, the exponent changed by 1 when we took the derivative. It's always going to be 1 difference. So I got to be honest, I don't spend a lot of time thinking about them anymore. I just know it's 1. You know, you can think about it if you want, but I just know this one is going to be 1. What's left over here? Minus a half x. And after that, life is a lot better. I almost said simpler, but maybe simpler is not the right word for what's going on here. Let me do some tidying up here, and you can tell me what you think. Okay, so that's still up in the numerator. My square bracket's still up in the numerator, and I get 1/2 x plus 1, because x minus a half x is 1/2 x. That's still up in the numerator. Down the denominator, I have x. I have x plus 1, and I have, this root x plus 1 that I just discovered from the, let me just highlight it so you can see where that came from. Sometimes when I do these, it's difficult to keep track of where everything went. That went to there. That went to there. Is it x plus 1 to the negative 1/2 down there? Okay, yep. And I can do a little better. Those happen to go. The 1/2 and the negative 1/2, those go. And so I get this. Sometimes textbooks prefer that you pull this off, like this. Because isn't that nice looking? In the next chapter, we're going to go, okay, when is this thing equal to 0? When is it undefined? All these things. And isn't this set up nice to do that? And that's where they're aiming towards. So these questions where people are like, how do I know when to stop? It's hard to know in this chapter where to stop. But next chapter will become clear where the great stopping point is. And the great stopping point is when you could just pick the zeros off just by looking at this thing. Questions about that mess. In the middle of the lawn lesson. In the middle of a beautiful lawn lesson. A tough derivatives from the tough derivative lesson. And I think if I was asking a tough derivative, that'd be as far as I'd go with a tough derivative. Maybe because I think the ones that had 2s and 3s in the numerator and denominator, they weren't as tough. Once you did a few of them, they weren't as tough. So you could imagine something with 2s and 3s in it as well. Questions though? I saw some frowning. It was just in general frowning, not specific question frowning. More time there? Oh, I'm going to put a check here. I'm going to put a double check there. But I'll take this, but we're moving towards maybe this a little bit. More time? Who needs more time? Isaac, more time? Bring this out because that's what you're talking about next. Right? More time? We're good? Here's the other proof. Here's the other proof. Bring your brain back to the proof there. It's going to get 5 stars at the end. It's this one or the other one. We'll go through this whole thing again like you've never seen it before. It says, what if the base isn't e? What if it's log base a? Yeah? So what we're after this time is the proof of log base a. See, we already did log base e, which is ln of x. On the off chance, and this isn't being insulting, on the off chance you get all this way and like, I keep writing this thing down that's ln. I don't even really know what it is. It's just keep writing ln. It's just log. But base e, we did log base 10, log base 2. There's also log bases. Log base e is a very common base to use. It's called the natural log. It's a natural one to use because of its beautiful derivative. Derivative ln x, 1 over x, so good. Making you brace yourself for this one. No, but look, this derivative has the 1 over x, but then for some reason a factor of ln a pops into all this. I'm going to do it here. Okay, here's what I love about this proof. It's got lots of stuff going on. First move. Y equals log base a of x. I'm going to move the log base a over here. Let's just talk about that one more time. Adding becomes subtracting. Subtracting becomes adding. Multiplying, dividing. Dividing, multiplying. Squared, square root. Square root, squared. We've got all these inverses we've been using all the way through. And the one you have to get to know is log base a, when it moves over here, becomes a to the power of whatever's there. Why is that such an unbelievably good move? Because we know how to take, from yesterday, we know how to take this derivative, a to the y. So what I'm going to do is take the derivative with respect to x of both sides. And from yesterday's lesson, we found out that if the base isn't e, it's some other number like a, so it could be a 2, a 7, an 11, a 10, 55, 1.06, whatever. If the derivative's not e, you still take the derivative and you still do a to the y. But then there's something else. What's the something else? I'm hesitating for so long because I'm worried. I'm worried. I'm not angry. I'm not hurt. I'm just worried that we're a little behind in homework. And I'm trying to decide what to do about that. Is that there just hasn't been enough time. And now this homework, which was the last lesson from yesterday, no one's looked at. And I was waiting to see what the hesitation was. But Brad has the answer. Ln a. Okay, so important if we're going to do this proof that you know that. Let's go back to the first proof. The first proof, at that exact same moment, when we took the derivative of e to the y, it was just e to the y. It was so nice. If it's a to the y, you got to know the ln a is coming. Here's the nice thing about proofs and why I grew to love proofs in university. It tells me. Yeah, if I forget it, it tells me. Like if I get all the way to the end, like, oh, I missed something. You can, where does it go? So there's like a hint in this whole thing with proofs. So it's sort of nice. I like proofs. This side, derivative of, sorry, I got so carried away, I forgot something. A to the y, ln a, now derivative of the inside, the chain rule there, and that's where I get my dy dx. A dy dx has to pop out if I'm going to get the answer here. And then I'll go up here, just some isolating, dy by dx, divide by that big mess, a to the x ln a. And it's nice. It's good. It's got a to the y, sorry. A to the y. Ln a. Yeah, there. It's nice. It's good, but it's got y's in it. And we'd really prefer something with x's in it. So this a to the y has got to go. So I look back through to find out what a to the y is. And lo and behold, there it is. A to the y is x. This becomes up. And then dy by dx equals 1 over x ln a. 5 stars. See, we didn't do the proof section too much in this quad. But maybe here's a chance for me to just nudge a proof in here and actually give you a nice gift. At least 3 or 4 of the marks, I don't know I'm going to make it out of yet. I haven't added up the test and worked it out yet. At least 3 of the 4 marks, you're like, okay. Just got to work on those 2 and I'm ready to go. There's 3 of the marks taken care of. Questions about that, baby? Hopefully, on a scale of 1 to 10, the first time I explain it, you're like, I'm like a 5. I sort of get it. And then hopefully, the second time through, you're like a 6 or a 7. You're like, okay, can sort of handle these steps. It's so good because it's got inverses. It's got implicit differentiation, and it's got some subbing. It's a real good setup. It's a real good introduction to proofs. Here's how the regular questions in the homework are going to look, though. It's going to ask you stuff like this. Differentiate log 3x plus 1 to the 4th. And for a lot of people yesterday, what I was suggesting was when you get ones like this, it's just take it a piece at a time. Start covering things up as you go through. So this is log of 3x plus 1, but the power of 4 is outside, is there, so it's on the 3x plus 1. So really when I do this y prime, I'm doing 1 over that mess first. And I'm going to completely forget to do something, because it's the mistake you're going to make. There's this mistake I'm making right here. I'll do the rest of it, and then we'll see if anyone's caught the mistake already. I've already made it. Times the derivative of the inside. The derivative of the inside is 4 bracket 3x plus 1 cubed. Times the derivative of the inside again, 3. This thing simplifies so nicely. And yes, I still forgot that one thing. I've given you lots of time to try and think over, what did he miss? And this happens with log and ln derivatives all the time. When it looks ugly and the exponents get big for a minute, and then suddenly they're just not. It simplifies down so nicely when you follow through. So what did I forget? If Brad has the right answer, it's 2 parts. He's going to say one thing and then say the other. Do you know what I'm talking about? Say the first part first. Ln, yeah, okay. So when the derivative isn't ln, you pay the penalty. It's like ln comes back to haunt you. You're like, oh, you're not doing ln? Oh, I'm coming anyways. Your answer is going to have ln in it. What's the base here, though? 10. So ln 10 there on the bottom, and ln 10 there on the bottom all the way through. So when the base isn't e, you always pay this penalty of the ln factor in there. Where does that come from? It comes from the proof that I did yesterday of a to the y. Next question, find the equation of the tangent. Again, these have 3 steps. When it says equation of tangent, if you're still having trouble with all those steps and you're worried about it on a test, write down the 3 steps. We're going to take y prime. We're going to find m tangent. And then we're going to do y equals mx plus b. So there's 3 steps to get all the way through this question. And it's easy to forget those steps as you're doing crazy derivatives and so on. Derivative of log base 2. Y prime is 1 over x long pause to what you think. Maybe I've given it away by leaving an open space in the denominator there. 1 over x since it's not base e, since it's base 2, ln comes back to haunt you, and it's there in. But that was all. Yeah? Derivative of the inside is just 1, so there's a nice y prime. So therefore, m tangent equals 1 over 8 ln 2. I sub the x in and get that m tangent. Now I'm done step 2. And so y equals mx plus b. If you're using other versions of the equation of the line and you love it, go ahead. I'll keep going back to y equals mx plus b because I don't want those other equations of the line to be the part that confuses you here. So y equals 1 over 8 ln 2 x plus b. These get weird, right? You know, because they have the weird slopes and weird numbers you're subbing in. They get weird looking. So then sub in 8, 3. 3 equals 1 over 8 ln 2 times the 8. And so b is 3 minus 1 over ln 2. Therefore, equation of tangent is y equals, what was the slope? 1 over 8 ln 2. X, and then a weird y-intercept of 3 minus 1 ln 2. 1 over ln 2. 8's cancel. 1 over ln 2 over 3 minus 1 over ln 2. Bring it over. Yep. I did those fast. I'm not saying they're easy. I was trying to focus on how important those 3 steps are. 1, find y prime. 2, use that to get the slope of the tangent. And then 3, do y equals mx plus b, subbing in the point you were given to finish off the equation of the tangent. What questions do you have about that one? Questions? More time? Who needs more time? More time? All right. Still more time? Now that you had time to copy it. Questions? Who's got questions? What's left? One last slide. I don't even remember what's coming next. Oh. This is so important. I'm almost willing to give away the test question. I'm pretty much going to give it away. See, there's good and bad things about giving away a question on the test. When I tell you, oh, it's going to be this proof, or the other one, you don't spend a lot of time learning a whole bunch of other stuff maybe, because you know what's coming. But I've got so much focus on this that I hope you learn what this is all about. It's worth it. It's a payoff for me. I'm like, oh, they get to learn that, and they get the marks out of it. It's beautiful. The question on the test will be so shockingly close to this. I might make it x to the x plus 1 or x to the 2a. It'll be something like this. You have to deal with x. Okay, why this is such a big problem. You have to understand why this is such a big problem before you can even start the question. You see, we've got some nice rules now. We've got a rule for when x is the base and the exponent's a number. Oh, no, I don't care. I just thought somebody was looking for me or something like that. You see, here's what we've learned. Situation 1. Y equals x to the n. You see? And by putting an n up there, we're letting everybody know that's just going to be a number. A 7, a 2/3, a -5, whatever. There's going to be some number up there. And we want to take that derivative. We just bring it down and reduce it by 1. Okay? Fancy notation to describe what we learned about power rule. But we didn't make a big deal out of it. But the important thing about power rule was variable in the base, not variable in the exponent. Some number. Yeah? Yesterday we learned how to deal with y equals a to the x. And this is trying to say we've now reversed the 2 roles. Variable up in the exponent, constant down here, some number, 2, 4, 7, whatever. Okay? So these are like, and then its derivative is a to the x ln a. Is this situation clear? We've now dealt with if the variable's in the base or if the variable's in the exponent. 2 separate ways to do the derivative based on where the variable appears. Then this thing comes along and goes, oh yeah? You want to play, huh? All right. How about if it's a variable both places? Y equals x to the power x. And actually, they don't get a lot harder than this one, no matter what those two things are. If there's variable here and variable there, you've got to use the method called log. Here, I'm going to highlight in blood. This is AP stuff. Like this is the kind of thing, the regular calculus course, we don't get to at all, but you're going to be ready for it when your prof breaks it out next year, because of this moment where you go, okay, there's three kinds of basic derivatives. X to the power of, something to the power of x, and then x to the power of x. Whole new ball game. It's not bad though. Here's the thinking. We wish that x wasn't up in the exponent like this. We wish that it didn't have variable with a variable up there, and there's a beautiful way to take care of this, and it's so good. I'm going to write it in this line in red. I encourage you to write it in another color, or highlight it, or put a big box around it, or one of those tabs that sticks out the side of your page, because not just how good the move is, but how important this move is. I'm going to take lns on both sides. And then I'm going to let that just sit for a while, because I hope what happens to your brain is one or two things. You're like, oh, I know what's going to happen. Or you're like, I have no idea what you did that. If you're in either of those two situations, we're in great shape. Either, oh, I know what you're going to do. Or you're like, I have no idea why you would do that. Because either way, something big's about to happen when we explain the next step, and then you'll be ready for this situation. Does anyone know what's going to happen next that completely changes the nature of this question? Simon. Yeah, it's so good. It's like equations are impossibly complicated because of the variable up in the exponent. That variable up in the exponent makes these things really, really difficult. And then Lon puts up his hand on the back and says, hey, I can handle this. I got this. You get Lon involved, and Lon goes, yeah, I'll just bring it down. It's no problem. The rest, I won't say it's easy. There's nothing easy left in this world. We get this far, there's nothing easy. But the rest is pretty straightforward in that we go, okay, we just do this, we do this, we do this. I'm now going to do d by dx of both sides. And I'm getting really dramatic about doing that, even though that particular line only describes what I'm about to do. It doesn't actually do anything, except now I'm going to take the derivative. And I'm going to go back to not red colors because, well, I'm pretty unhappy with the space I have here. Just give me a second to tidy some things up here. We'll just lock that stuff, and we'll just grab that pile of stuff and just, hey. Hey, grab it. No, you silly. Go. Okay, how about this? No, all right. Sorry, it's got to go. I hope you got it copied down, this stuff, because it was important, but it's all got to go because it's in my way now. Bye-bye. See you later. Okay. Derivative of ln y. I'm going to do that side and then pause and wait for either nods or frowns, okay? Derivative of ln y with respect to x. Nods? They're okay over there? Derivative of x ln x. Derivative of the first times the second. Plus derivative of the second times the first. This literally was the example from earlier. Warming you up for this thing. Okay, how do I do? Derivative of the first times second. Derivative of the second times first. Tell me. Is this okay? dy dx. The 1 over y there is equal to, let me tidy this up, ln x plus 1. Two last steps, dy dx equals y ln x plus 1. This is a good answer, but I'm not going to put a check mark beside it because I don't want to call it good anymore. I'll put like the half smile face, like, it's good. It's good. It's good. It's good. We can do so much better. Easily. So much better. Who's got it? What can I do now? Just to make this even more pretty. It's almost all x's. It's x, 1, yeah. This y sticking in there, and the derivative of y. Not super convenient. We want to set this thing up so if someone's got an x, they can just sub it in there. Yeah, you see? Comes back. You know, you get down and you're like, well, why is there y in there? Meanwhile, the algebra screaming at you. Yeah, look, me. Yeah, I got it. dy by dx equals x to the x times ln x plus 1. You know what? It's not, compared to some of the derivatives we've done, look at this final thing. Like if you had to sub into that, like, oh, that's not too bad subbing. Sub into 2 to the 2, ln 2. You know, it's not the most complicated derivative at the end, but it comes from a really nasty function. It really is nasty. Like compared to x to the 4 or 2 to the x, this thing's nasty. It's trouble. And like I say, ln's there to go, I got it. Let me just break this thing down for you. And here we go. Yeah? Questions about that? Making these videos, I used to have all these funny sayings I use. I can't use in the videos anymore. I used to think that was funny. Everybody laughed at that, but I'm going to put that on videos, yeah? I don't know why that's funny to me. Hey, you got a question on this? Yeah. Something like that, where you got to use logarithmic differentiation. It's worse than that. It's not just that you have to use logarithmic differentiation. You have to be able to recognize it's time for it. Variable to a variable, you're like, ln. Yeah? Okay.